Now, what is a nested function? This is not a very complicated. All of you have seen it in high school. So you have one particular z computed from x, right? Z is a function of x, right? And then you get this z, and you pass it through another function. You compute y. Now, does y depend on x? Yes. If you change x, z changes. And when z changes, y is going to change. This is what we call it a nested function. So y is a nested function of x, because you can write it down in this form. Y depends finally on x, right? Through z, of course, but it's going to depend on that, right? Another question is that you have done this in high school, I'm pretty sure, that how you can compute the derivative of y with respect to x. Anyone has any idea? You use the chain rule, right? You're going to say derivative of y with respect to z, and then derivative of z with respect to x, right? Where does this come from? I mean, again, I think that most of you had seen it before, but just to recap and make sure like everybody is in the same line, because this is going to help when you want to do it for more complicated cases. We can think like this. We could say, okay, if we remember the definition of the derivative, if we change x a tiny bit, at the end we want to see how does this y going to change, right? When I change x a tiny bit, say dx, then the change in z, I can write it down in this form, right? Derivative of the function times the change in x, right? So it's going to be g prime or g dot times dx, right? Now, I have known the change in z. Now, I want to know from change in z, how does y change, right? So again, I'm going to say, okay, if I change z with dz, this very tiny bit, then the change in y is going to be derivative of the function times that dz, right? Everybody's clear? Right? Now, what you're going to do, you're going to get this dz from this expression, replace it here. You would say that the change in y is going to be derivative with respect to z times derivative of z with respect to x times dx, right? And this is the chain rule that you have, right? So you can always think like that, okay? This x is changing. Now, it's going to change everything next to it, right? And if you just formulate those changes, then you're going to find out what is the change in the very, very output, right? So that is what we call it the chain rule. So you can write it down in different forms. For instance, you would say, okay, dy is going to be supposedly the derivative of fg times dx. And then when you compare these two, you would say that derivative of y with respect to x is derivative of y with respect to z times derivative of z with respect to x, right? Everybody remembers that, right? Everybody's cool. Yep? Questions? So you can actually do it in a general case, right? Much more complicated. You could say that, okay, I have x, and then this x goes and compute z1, right? z1 goes computing z2. z2 computes z3, and so on till you get to zn, and then you want to get to, you compute y. Now you want to know, how does y change if I change tiny bit x? So if I change tiny bit x, I'm going to change z1, and then z2, and z3, and all of this change is going to propagate forward till it's going to change y, right? So I can write it down in this form, so I can start from very end. I would say, okay, dy to dz, the last z, right? And then the change of the last z, dzn, with respect to the previous one, dzn minus 1. And you keep on just writing it down towards the very beginning. So you're going to get dz1 with respect to dx, right? And this is the chain rule, like the very deep chain rule, right? Everybody's cool, yeah? Now, the reason that I showed this is because we can actually show everything in the form of what we call it a computation graph. And this is eventually the thing that your computer uses when it wants to compute gradient, okay? Now, the whole purpose of talking about the computation graph is that I want to build your mindset about the gradient or derivatives. You should change it a bit when it comes to neural network, because for many of you, I do know that simply derivative is a functional operation, right? So it's going to get a function and gives you another function, right? But this is not the case on your computer, right? What happens in your computer, you're going to have one variable x, right? And all of these functional operations that I told you, they're going to be a bunch of functions in your program, right? So x variable goes in, the first program runs, it's going to compute one z1, right? And then z1 is your next variable. It's going to go to another program. It's going to compute the next variable, right? Till it's going to get to y, right? Now, on your computer, what are these guys? X, z1, z, and y. What are they? Are they symbols? No, they are numbers, values, right? They are saved on your memory as values. Everybody's clear, right? So this functional operation that you have, it can only operate when you give it a number, right? So you say x is 2, it's going to compute z1, right? Once z1 is, for example, 8, then you're going to give it to the next program, it's going to compute you z2, right? And so on. Everybody's clear, right? Okay, now what you can say that when I have this computation graph, the thing that I want to do, I want to just get back to x. I want to see if I change x a tiny bit. I told you x is 2. What if I make it 1.9 or 2.1? What's going to happen? I want to understand that. So I know this tiny bit of change in x, right? Now, if I want to know how does y change, so I need to know its derivative, its gradient. And you can compute it again using chain rule on this computation graph. So you would say that whatever the change in y is, that can be written as the derivative of that program, that function f, times the change in zn, right? And then you can again write down zn with respect to zn minus 1. You can keep on going till you get to the very beginning, right? So your derivative of y with respect to z1, you can write it down as multiply of all of those previous derivatives together, right? And then if you want to know it with respect to input, well, you just need to move backward from very beginning towards the, from very end to the very beginning. And then you just multiply every gradient that you computed, right? Everybody's clear? Sorry? Here we have just a scalar input. We're going to extend it. Right now, everybody's scalar, simply. Everybody's cool? So let's look at one example. So say we have this particular example. z1 is 2 times x. z2 is z1 squared. z3 is e to power z2. And y is log of z3. Okay? Now, first of all, can you tell me what is y in terms of x? I just want to keep it here. What is y in terms of x? z3 is e to power z2, right? When I take the log, it's going to be z2, right? So y is z2, right? And then z2 is z1 squared, so y is z1 squared, right? And z1 is 2 times x, so it's going to be 2 times x to power 2, so it's going to be 4x squared, right? So y is 4x squared, right? Everybody's clear, right? So you can compute the derivative, right? The derivative of dy with respect to x is 8 times x, right? So that's it. So this is y with, in terms of x, and you can directly compute the derivative, right? But we are thinking that we are doing it on a computer, right? And your computer doesn't understand what is x, right? Whenever you give it a value, then it's going to find out what is the corresponding value for z1, z2, z3, and y, right? Everybody's cool, right? So your computer, what it's going to do, it's going to build this computation graph. It's going to say, whenever you give me x, I can compute z1, I can compute z2, and so on till y, right? So what you do, you're going to define in your program x equals by, for instance, half, right? X is half. Then what is going to happen? The first program going to compute z1, it's going to be 1, right? 2 times half is 1, right? The second program going to get this 1 and square it. It's going to be 1 again, right? The third program is going to get this 1 and take it to put it in the exponential form. So it's going to be e, right? And then e is going to go inside the last program, which is computing log, supposedly in the natural base, and it's going to give you back 1, right? So this is how your computer works, right? So you give it half. It computes every single variable in between until it gives you 1, right? Now you want to know what is the derivative of y with respect to x, right? Now, derivative of y with respect to x in your computer is not 8x, right? What is it on your computer now? Can you tell me? It's derivative of y. If your computer could compute the derivative, what it would be? What is the value of x on your memory? Half, right? What would be the derivative for your computer? 4. So derivative is not 8x. 8x has no meaning for your computer, right? The only thing that your computer understands is that when you give me x, I should be able to compute 8 times that to give you the gradient, right? The gradient or derivative for your computer is simply, at this point, 4. If I change x to be 1, it's going to be 8, right? You see it, right? It's about numbers. It's not about symbols, right? Symbols are abstract mathematical objects helping us to understand things easily, right? On the computer, they do not exist, right? Everybody's cool? Now, what does your computer do then? So your computer is going to do like this. So it's going to say that, okay, this was the graph, and if I want to move back, I need to know the program which is computing the derivative of every single edge, right? So if I have z3, I compute that, I put it inside the log, I'm going to get y, right? Now, if I want to get back from y to z3, it means I want to know what is the derivative of y with respect to z3. I'm going to get this z3 and put it in denominator, right? Because derivative of log is 1 over the argument, right? So you have your original program, which was computing the way forward. Now you have your other program, which is defining the way backward, right? Everybody's clear? Questions? So your computer can build these guys because eventually it has these programs. It's like whenever you write your code, you write f, and you write next to it is f prime, right? That's it, right? Now, it has f, it has f prime. It wants to know how it can compute the derivative of y with respect to x. Well, it's going to say that these are the variables for me, right? Starting from beginning, I was half, then it becomes 1, 1, e, 1, right? And now I just need to move backward, right? So 1 over z3, if I give z3 value to it, it's going to be 1 over e, right? 1 over e. This is going to be the derivative with respect to this node, right? What about the derivative with respect to this node? I'm going to look at my reverse, my backward function. It's e to the power z2 here. z2 value is 1. This means that 1 goes inside the second program, and it's going to give me e, right? So the derivative of y with respect to this guy is 1 over e times e. It's going to be 1, right? And it's going to keep going backward till it gets to the very beginning, right? So it's going to just compute everything towards the end. So for instance, derivative with respect to z3 is going to simply be 1 over e because z3 is e, and the backward function is simply 1 over z3, right? Derivative with respect to z2 is going to be this 1 over e times e, right? Derivative with respect to z1 is going to be this last term you computed, which was 1, times this new term, which is 2, right? And so on till the very beginning, right? Which is the same thing as you put x half here in this functional operation, right? Everybody's cool? Do you see that? Okay, so this is the way that your computer is going to compute the derivative. And this is the most efficient way because, as you can see, you don't really need to think about the whole process, right? You just need to be able to compute locally the derivatives, right? And that is not a hard thing. If you're writing the code, you can always define the forward and backward function, right? If I know that in the forward operation I'm just squaring something, in backward operation it's going to be 2 times the same variable, right? So these are the two functions that I have next to each other. If I do have them, then I can put them on the computation graph and compute the derivative of any node with respect to any other node, right? I just need to start from that node, move backward till the other node that I want, right? And multiply everything. This is going to give me the derivative. Yes? Yes. This is the one which we are going to talk later. Yeah, we are going to compute it all over the neural network to see it. But the key, short answer, your activation function, whatever that is, you can always define its derivative, right? It's a ReLU function. I'm going to define the derivative to be this step function. That's it, right? Right? And now, the next thing is that what about those weights in between, right? But again, those weights in between are linear functions, right? So your output of that layer is a linear function of the output of the previous layer, right? And then you can just take the derivative of a linear function. That is, again, something that you simply can define, right? Everybody's clear? You clear? OK. Questions? No question? OK. So now, one thing that I want to indicate here, so I hope that you get this very clearly, that gradient computation here is just a computational operation. You should not think this functional way that you are used to when you are thinking about mathematical derivative. And when you want to compute the derivative of one function on a computation graph, you should definitely start by going forward, right? If you don't go forward, you don't know what are the values of z1, z2, z3, and y, right? And if you don't know them, you're not able to compute the gradients, right? Because you are able to compute the gradient when you know those local gradients. And to compute those local gradients, you need to know the value of the variables, right? So if you are doing it on your computer, you should definitely first take the forward pass, and then you can move backward, right? Meaning that on your neural network, and you're going to do it all the time, whenever you want to compute a gradient, you need to first put your data in the input. You just compute every variable in between till you end up, right? Once you ended up, your computer just builds a computation graph, right? And it starts to compute local gradients backward, right? And then it's going to give you, this is the back propagation, it's going to give you the final gradient that you want, right? So you cannot do it like, I don't know, probably you had this idea before, those who had been involved with implementing neural networks. But if not, this is the reason that you always need to first just write the function forward, right? You always write forward, you pass everything forward, so that your computer can build the computation graph, and then you say, just go backward, right? It's going to do the autograd, it's going to do these operations in the behind the scene, right? And then it's going to compute the gradient. Everybody's cool? Yes.
So the backward is the computer will start from the last one, find the derivative function, and plug in the number to the derivative function,
yes,
and use that value as the second last.
Yes. Yeah. So we're going to compute the first one, last gradient, the second last gradient, and so on, and multiply them next to each other till it gets to the destination that you want, right? OK. Everybody's cool? Yes? Yeah, we're going to do that. No worries. This is just right now. It's just a simple example. We're going to do it for a general case with a vector matrix. No worries about that. Questions? OK. So, yeah. OK. Let me just. Is it OK that I just go over it quickly, 5 minutes, and then we have the break? OK. So we can extend this idea to the case where we have multivariate functions involved. For instance, say that I have multiple values of z computed in parallel, right? You have x, it computes z1, z2, z3 till last z, right? And then all of them together are going in a multi-dimensional function f, giving you the value y, right? Now, again, you want to know what is the derivative of y with respect to x, right? And now it involves lots of variables in between. How you can do it? Well, you can simply say that every single z that I have in between If I want to know how does it change, I just need to know the derivative of the function connecting it from x, right? So derivative of z is going to be basically the derivative of that particular function, right? Now, you have all of these guys. So you have d of z1, d of z2, until d of zn. And now you want to know how does y change. What should you do? Look at this f. If it is a multidimensional function and you have a tiny move inside the input, how do you compute the change in the output? We talked about it. Partial derivatives, right? You compute the gradient, do the inner product with the vector of changes, right? So you would say this function f is a multidimensional function of a vector z. So if I have a change in z, which is dz, and every single change is given by this expression, right? I just need to inner product the gradient with that vector of change, right? So meaning that I take y, I compute the partial derivative with respect to the first argument, I multiply it with the change in the first argument, plus derivative of y with respect to second argument, multiply with the change in the second argument, right? And so on until you're over with all your arguments, right? Everybody's clear? Okay, so this is going to be the partial derivative of that function after, and then you put that partial derivative also for dz, you are going to write it down the derivative of g times dx, right? And then it's again the vectorized form of the chain rule that you had in the earlier courses, math courses, right? So how you can express it, you could say that, okay, if I have this multidimensional function which has n different variables, now if I want to know what is the change or derivative of y with respect to x, I could start with the arguments inside the function, right? Because y is given as a function of z. So I'm going to say that y is going to change with respect to the first argument, multiply with the change of the first argument with respect to the target variable, right? Plus d of y with respect to z2 times dz2 with respect to dx, and you go on, right? Whatever variable you have, you should take that derivative into account, right? And this is the vectorized form of the chain rule. Everybody's clear? Now, we can again put it on the computation graph. How can I do it? I can say this is x, right? Then I have n different functions, right? N different functions computing in parallel n different values of z, right? And all of these z values go together into one function f, which is computing y, right? All of them go inside y, f, to give you y, right? Now what you want to compute? You want to compute the derivative of this y with respect to x. What should you do? You should move backward on this graph, right? So I would say, okay, I do know what is the derivative of y with respect to the first argument. I can write it down, right? I am the one who defined function f. I can also define the first partial derivative, right? I can define the second partial derivative. I can define the last partial derivative, right? And now these partial derivatives are going to give me the power to compute the derivative of y with respect to every single variable in between, right? Now, I want to get from that node to the input node. So what do? I again look at this z, and I am the one who has defined this gn, so I can write down the derivative function as well, right? Same thing I can do for everybody, right? Now, if you want to compute the derivative of y with respect to x, what do? You're going to use the chain rule, right? So you're going to say that, okay, I'm going to get this f1, whatever that is, I'm going to multiply it with g1, right? This is one of the terms. f2 times g2, so on till fn gn. And I add up everything that is coming in x, right? When I add up everything inside x, then I'm going to have the derivative of y with respect to x, right? Again, there is a computation graph. Again, you start by putting x there and compute anything after that. Once you have those values, you're able to move backward, right? So you can compute all the derivatives on the edges, and then you can add them up when you are ending up at x, right?